Alright, hey everyone. So today we'll be talking about Lenz's law and magnetic flux. So just to give an official definition of Lenz's law. Lenz's law is the direction of the induced current will be to minimize the change in magnetic flux. Now, just to put that definition in sort of simpler terms, just as a mass m resists changes to its velocity, conducting loops like the ones we have shown here resists change in its magnetic flux. Now, magnetic flux, its formula is known as the integral of B times dA. Now, however, we're not going to be concentrating on the calculations of magnetic flux in this video, because that is more involved in Faraday's law of induction, which includes d-flux, which hopefully another group will cover in their video.
Alright, so our first problem is basically we have a bunch of conducting loops, a bunch of conducting loops with a current that is increasing or decreasing in some direction. So in order to solve these problems, we have to talk about the right-hand rule. So we know that a current will induce a magnetic field, and we can figure that which direction the magnetic field will be induced in with our right hand. So if we have our thumb pointing in the direction of the current, and then we have our fingers will be the magnetic field. So for our first one, we have the current is increasing in the left direction, and the magnetic field will be going into the page, into the board. So based on that, we have an increasing magnetic field into the board. So based on Lenz's law, the current induced will oppose that. So if we use our thumb as the magnetic field this time and our fingers as the current induced, we know that it has to go out of the page to oppose the increasing flux into the page. So then we get an induced current clockwise. For this problem, we have current going this way and magnetic field going out of the page, but this time it's decreasing, meaning the change in flux is into the page. Therefore, to counteract the change in flux into the page, our magnetic flux needs to be out of the page again, so our induced current is again clockwise. Okay, so then we have a problem with constant current. So there's no change in magnetic flux, and because of this, there's no induced current in the loop, because induced current is totally based on change in magnetic flux. And then for our last one, we have current increasing up, and then we have our magnetic field, which is into the page. And to counteract that, we need a magnetic flux that's out of the page. So we go up with our thumb, and then we get it clockwise again. Alright, so
now we have just a couple more examples involving bar magnets, magnetic flux, and induced currents. So for this one, we have a bar magnet, again with north and south poles, which has a magnetic field B, which is actually moving closer to this loop that you see here. And again, following the Lenz's law properties that we just described in the previous example, since the bar magnet is moving closer to the loop, we have more magnetic field, think of it as more magnetic field lines that is actually pushing into the loop. So in this case, we'll have, again, an induced current that's coming this way around, and in this case the magnetic field will be increasing, and there will be a greater change in magnetic flux. But sort of a foil to that is this one. Here we have a similar example, but now the difference is we have the bar magnet is actually moving away from the loop. Same properties, a north and south pole, same magnetic field B, but this time we're moving it away, as you can see here. So what changes is we have a different direction in the induced current, similar to what we described before. Now this is very important, because we want to show what happens when we do not move the bar magnet at all. Because keep in mind that the area of this loop stays the same, and the strength of this magnetic field stays the same. The only difference now is that this time there will be no induced current, simply because we are not moving this bar magnet at all. So we have a set number of magnetic field lines actually going through the loop, and because there's no movement in the bar magnet, there's no induced current produced.
Yeah, so for magnets in general, each magnet has, they're all dipoles. You have a north and a south pole. And this is like an intrinsic property of physics. Scientists have yet to uncover a monopole. But essentially, if you divide this magnet, if you cut this magnet in half, like I sliced it here, then you're gonna have two magnets that are dipoles. So this will create a south pole and this will create a north pole. So you can never get a monopole just by cutting a magnet in half. And pretty much a magnet is one pole is the north pole, and that essentially has magnetic field lines going outwards, and this is essentially magnetic flux. And then the other side is the south pole, where all the magnetic field is going into the magnet. So this creates like a magnetic field around the magnet. Alright, thanks for watching.